Okay. Yeah. So what we actually learned in the last class is that the first law of thermodynamics, that is the conservation of mass and energy principle. So we have seen this principle on the control volume, means on the open system. So in open system, so as we all know that there will be mass interaction as well as there may be energy interaction. So when we considered an open system, so in the inlet we consider one section 1 1, and at the outlet we consider another section 2 2. Okay, then we consider the mass flow rate as dm1 by dt, and in the outlet as dm2 by dt. So the amount of substance which is going out from the system minus the amount of substance which is going inside the system through the inlet or through the section 1 1 will be equals to the amount of substance which will be accumulated inside the system. So this is the principle of mass conservation. Then if you just assume that there is dq by dt amount of heat. Why it is dq by dt? Because this is a continuous process. That is why with respect to time, the other parameters are actually considered, or other parameters are measured. Okay, so it is a time variable. So we are not considering any space variable. This is time variable. So that is why this dq by dt term is considered instead of writing directly q or w. So dq by dt amount of heat rate, it is interacting with the system, and dw by dt amount of work, it is interacting with the system. Okay, and finally when we balance the energies, okay, means we actually place the energy principle, finally what we got, so we got this equation. Okay, we got this equation, and here you can see this is w1. Okay, so this w1 is nothing but the mass flow rate, so dm by dt. Okay, dm1 by dt, this is small w1. So sometimes in some books when you will be solving some problem, or when you will get some derivation, when you will see some derivation, so instead of dm by dt, so you will get w1 and w2 instead. Okay, so here this equation, all of you should remember this one. So here you can write h1 as the first term. Okay, then v1 square by 2 or c1 square by 2, because I told you that if you write c1, then you will not get confused actually, because v is written for volume. Okay, and small v is written for specific volume. Okay, so here capital V, it means the velocity, okay, at the inlet. So h1 is what? This is the enthalpy. H1 is equals to u1, small u1, plus small p1 and v1, small v1. H1 is the enthalpy, which is the summation of the internal energy and the multiplication of pressure and volume. Okay, so here it is specific enthalpy. Understood? So joule per kg, this unit is joule per kg, specific enthalpy. So we have seen all the units of this equation. Okay, so dq by del tau, here instead of dt sometimes you may get p tau also. Okay, so tau also, it stands for the instantaneous time. Okay, tau equals to w2, that mass flow rate at the outlet, and this is similar to this one, only the suffix are replaced by 2 instead of 1. Okay, because this is for the second section. Okay, 2 to section, and then finally you need to write the work in direction. So dw by d tau or dw by dt. Okay, so they have written Wx because they have considered the internal and external all the energies, and finally they have written actually Wx. So this means the W what we have taken as in the derivation. Okay, so finally, so we got this equation for open system, and this equation is called as steady flow energy equation. Okay, steady flow energy equation, and this is time basis steady flow energy equation. Understood? So now, if you just wants to write the mass basis energy equation, steady flow energy equation, then this one will be your mass basis energy equation, because what is W1? It is dm by dt. So mass basis will be dm by dm. So here that term is not written. Okay, and if the mass flow actually it is constant, okay, then we can write dm by dm will be equals to 1. Okay, and here also dm by dm will be equals to 1, so no need to write, but here dq by dm we need to write, and dw by dm. Okay, so this is the steady flow energy equation on mass basis, okay, or in mass basis form. Understood? So you need to remember these two equation, and this is the equation for open system or control volume. Understood? So now let's see the application, okay, of this steady flow SFEE, steady flow energy equation. So where you can apply. So as we all know, as because this is for control volume, so for open system, wherever there will be an open system, so we can use this concept. Okay, uh, so first we will see this SFEE on nozzle and diffuser. Okay, so what is a nozzle? So all of you have seen nozzle, isn't it? So there will be a small hole, and there will be a tapered cross section area. Okay, there will be a tapered cross section area. So you have seen, okay, these nozzles. In the pipelines also you may see in these nozzles. Okay, in your means in some practicals, physics practicals also. Okay, so when you did in your class 11 or 12, so you may have seen, okay, this nozzle, okay, or diffuser. So one pinpointed at the end, one pinpointed hole will be there. So through that hole, so the fluid will actually it will be flown. Okay, so what happens inside the nozzle? So here it is written that a nozzle is a device which increases the velocity or kinetic energy. Yes, because the velocity is increased, the kinetic energy will also increase inside a nozzle. So of a fluid at the expense of its pressure drop. Okay, so throughout each cross section, okay, so where there it is prismatic, means constant cross section, so you will not see that much amount of velocity, okay, inside the nozzle. But when there is a change in area of that nozzle, because at the end it is tapered, okay, and finally at the outlet there will be one small hole, so there will be a drop of pressure, okay, and the velocity of the fluid will be very high at the exit. Okay, so though it is it looks like that, as the velocity is very high, the pressure will also very high, like that normally workers said, isn't it? Workers say in the day-to-day life, we also say sometimes that when the velocity is very high, okay, so there is very high pressure, but it is not like that. So sometimes for nozzle, so here the velocity will be high, as because the pressure is dropped at the outlet. Okay, because there is a small area of cross section at the outlet. Okay, so the reverse case is for diffuser. Okay, so a diffuser, its cross section is higher, okay, at the outlet. Okay, means there will be a bigger hole at the outlet, and there will be increase in pressure, and there will be velocity drop. Okay, so kinetic energy will be dropped at the outlet. So that is a diffuser. Okay, so you should remember this thing actually, what is a nozzle and what is a diffuser. So what will happen when we will use this steady flow energy equation to a nozzle? Okay, so first we need to understand by pictorial view what is a nozzle. So you can see this diagram. Okay, so here if I will draw one line, so the left part it is a nozzle, and the right part, okay, so of this reference line it will be one what? Diffuser. Okay, so as because the nozzle, I have told you it is having higher kinetic energy. Okay, so what we can write, so in terms of this mass basis theory, so we can write the SFE in this way: H1, okay, specific enthalpy at 1 plus V1 square by 2, this is kinetic energy term per unit mass. Then Z1G means from a datum line, if Z1 is the elevation or height, not elevation, this Z1 is the height, then you can write Z1Z. Okay, then I have told you that there is no need to write dm by dt because this is mass basis equation. Okay, mass basis, I have told you. See, you can see this equation, or you can see this final theory, that there is no mass related term, okay, for this, because whatever mass it is entering, that same amount of mass it is leaving. Okay, means there is no change in mass inside the system, inside the steady system. Okay, so we need to write like this. Then dqm by dm means, here though this is insulated, okay, so nozzles and diffuser basically they are insulated, so this dq by dm, whatever heat that will be just transferring to the system, or it is producing by the system, so dq by dm we will write, okay, then h2 plus v2 square by 2, again the same terminology we will write on the right hand side, then dwx by dm. Okay, so instead of dwx you can write dw by dm also. It is also correct, because when we have derived, we have defined all these terminologies: what is w, what is q. Okay, so now you just tell me, so as the system, okay, as this system it is insulated, so will there be any heat interaction with the system? No. Okay, so there cannot be any heat flow to the system or energy flow to the system, nor there will be any work, okay, which will be producing or which you need to give to the system. Okay, due to its flow or its kinetic energy, so all the energy will flow with the fluid. Okay, means the energy which will be associated with will be directly the internal energies, okay, not the external energies like your dq by dq or like w. Okay, so here it is written, so here dq by dm will be equals to 0, as I have told, as it is insulated, and dw by dm will be equals to 0, and the change in potential energy is also 0. Why? Because the elevations are same. Okay, you can see this elevation, it is same, okay, at 1 1 or at 2 2. Okay, that is why there will not be any change in potential energy. If there is a change in datum height, then there will be change in potential energy, isn't it? So finally the equation will become what? So h1 velocity term will be there, h1 will be there, enthalpy will be there, the potential term will not be there. Okay, so you can strike out this potential energy term, then dq by dm will be equals to 0. Here also z2z will be equals to 0, and dw by dm will be equals to 0. So only you will see these two term on the left hand side and these two term on the right hand side, isn't it? So you will write this equation again. Then what this continuity equation gives? So this mass flow rate is what? In fluid mechanics also you have studied. Okay, rho 1 a1 v1 equals to rho 2 a2 v2. So what is v1? v1 is the velocity, v2 is the velocity at the outlet. So rho 1 a1 v1, instead of rho 1 you can write 1 upon v1 specific this one volume. Okay, so a1 v1, so this is specific volume, so a2 v2, this is specific volume. Okay, so we will be writing this as, when the inlet velocity, okay, or the velocity of approach v1 is small. I have told you that in nozzle or in diffuser, the inlet velocity, it is very very small. Okay, because in comparison to the outlet, the small orifice or the small hole, the entry level area of cross section, it is very much bigger, okay, or larger. That is why the velocity at the section 1 at this section, it is very very low. Okay, very slowly it will move, and finally it will move with a very high velocity due to this reduction in area, cross section area. Understood? So you can all physically feel this situation, and I think that all of you have seen this nozzle operation. Okay, so through nozzle, how this velocity actually flow actually happens, all of you have seen. Okay, and in fluid mechanics practical also, so you will see various examples, okay, of this kind of application where the velocity actually it is very much higher, or the fluid gets higher kinetic energy at another section. Okay, so finally you can write that this term will if you will strike out this term also, as because the inlet velocity is very very low, so only you need to write h1 equals to h2 plus v2 square by 2. Okay, so from here you can write the expression for velocity at outlet. Okay, means at nozzle the outlet velocity can be find out, okay, can be found out by this formula 2 under root 2 h1 minus h2, okay, meter per second. Okay, so suppose in fluid mechanics practical, if one nozzle is given and if you are asked to find out what will be the exit velocity, so you will be able to find out the exit velocity by taking the under root and the difference of the enthalpies, okay, of the inlet and outlet. But you should remember that these are specific enthalpies. Okay, and if normal enthalpies are also given, then also it will be having the same value, as because this is the difference. Okay, so if you write capital H1 also minus capital H2 also, and if you have the value, then if you directly put, you will get the difference, and if you multiply by 2 and take the under root, so you will get the exit velocity. Understood? So here h1 minus h2 is in joule per kg. I have told you this is specific enthalpy. Okay, this is not normal enthalpy, specific enthalpy. Okay, so this is one application of this steady flow energy equation for nozzle. Okay, and for this one diffuser, okay, for diffuser also, so you can actually apply the same concept. Okay, for diffuser also you can apply the same concept, but in diffuser what will happen? So this V2 term will be what? This V2 term will be 0. Okay, because in diffuser, so the velocity at the exit will be, it will be very very low. Okay, now you can take another application of this steady flow energy equation. So this is one open system or control volume system. This is called throttling device. Okay, so in throttling device what happens? So this throttling device looks like this one. Okay, so one inlet will be there, which is marked as 1 1, the cross section is marked as 1 1, and this is 2 2, the outlet is 2 2. Again, this is at the same elevation. Okay, and the surface is called as control surface. So for any control volume, as because the energy interacts to the surface, that is why the surface is called as control surface, but it is insulated. Okay, means no heat will enter and no heat will come out from the system. Understood? So flow through a valve. So this is one valve, throttling valve. So this is the valve, this is the schematic diagram of this valve. So with this valve you can adjust the flow. Okay, so this is half open. You can see there is a clearance in between this control surface and this part. Okay, so this is one nut like structure. So if you just release this valve, so it will be opened. Okay, so as because we need one operational throttling valve, that is why it is half opened. Okay, so what will happen when you will apply steady flow energy equation? So when a fluid flows through a restricted, okay, constrained passage like a partially open valve. Okay, so as you can see, this is partially open valve, and this is this area, it is, you can see this is constricted. Okay, so if you just open it totally, then you will get one open flow. Okay, so there will not be any restriction. So it is constricted passage. Okay, so like a partially open valve, an orifice, okay, or a porous plug, it is porous plug, there is an appreciable drop in pressure. Okay, so and the flow is said to be throttled. Okay, so where there will be a drop in pressure, so if there is an external interaction with the system, then that device is called as a throttling device. Okay, and that will drop the pressure a little bit. Okay, so shows the process of throttling by a partially open valve on a fluid flowing in an insulated pipe. Okay, the pipe is insulated, as you can see from the figure. Okay, so in the steady flow energy equation, so we will write dq by dm will be equals to 0, as because the control surface or the surface is insulated, and dw by dm will be equals to 0, there is no work production, or there is no interaction of the work to the system, okay, or from the surrounding. So you can write again that H1 plus V1 square by 2 equals to H2 plus V2 square by 2. Why I am not writing the potential energy here or energy term? Because these are placed at the same elevation, okay, or same height. From the datum line, the datum heights are same. H1 equals to H2. That is why I am not writing the potential energy term. Again, the equation becomes this one: H1 plus V1 square by 2 equals to H2 plus V2 square by 2. Now, for this pipe, okay, for this throttle valve, the velocity is very low actually. So the kinetic energy term, okay, is because there is a restriction, okay, in the very beginning it is stated this is constricted passage, okay. That is why the velocity at this inlet and the velocities at the outlet will be very low, and this results in less kinetic energy. That is why we can ignore the kinetic energy, okay. So that means H1 will be equals to H2. Understood? So the specific enthalpy at the inlet will be equals to specific enthalpy at the outlet, or the enthalpy of the fluid before throttling is equal to the enthalpy of the fluid after throttling, okay. And what is an enthalpy? So enthalpy is the energy of a flowing fluid per unit mass. All of you know this thing. So since no energy is imparted to or rejected from the fluid during a throttling process, its enthalpy remains the same. So for a throttling process, the enthalpy whatever it is at the inlet, so will be equals to outlet, okay. So this thing you need to remember, very important in competitive examination also. These things are asked, okay. So for throttling device, what is the parameter for from which the SFEE is actually analyzed from the enthalpy, okay. So from the enthalpy concept, so these throttling devices are analyzed on the basis of SFEE. Understood? Then you can see the application in turbine and compressor. So what happens in turbine? So turbine basically it is a device, okay. So in our plant, so these devices are installed to produce actually electricity, okay. So this turbine, they are having one shaft. You can see this shaft, okay, shaft or shaft. So this shaft, it is connected to a generator, okay. So due to the rotation of these turbine blades, with the help of this fluid, okay, it may be gas or it may be liquid, okay. So depending upon the nature of the power plant, so at the exit, the shaft will rotate and it will rotate the generator, okay. And the generator will be having some magnetic effect, okay, and that generator will be generating the electricity, okay, and finally which will be distributed to the this one bridge, okay. So what happens in turbine? So we are considering one virtual boundary, okay, as because any system it is having one boundary. So here, as because this is open system, so this is a imaginary boundary or virtual boundary. So this is the inlet of this turbine, okay. So one inlet will be there, one outlet will be there. It is directly not shown in the figure, okay. So there will be energy interaction, okay, as well as mass interaction. Understood? But this turbine it is insulated, okay. Means there will not be any addition of heat to the turbine, or there will not be any this production of heat from the turbine, okay. So whatever it will happen inside. So work we will get through this shaft, because the shaft is doing work. That is why so it can run the generator at the outlet. Understood? So if you just apply this steady flow energy equation, so you will see that the velocity, okay, flow velocities inside the turbine, it is very low, okay. That is why you can ignore the kinetic energy term, and the steady flow energy equation will become this one: H1 will be equals to H2 plus dWx by dm. I told you that there will not be any energy, means heat interaction, but there will be energy interaction only in respect of work, okay. So this work terminology will be there. So H1 will be equals to H2 plus dW by dm, okay. Don't write Wx, because in their analysis in this book, Pikenak book, so they have written this Wx, but in our analysis, so I have made it very simpler, okay, simpler form. So just you follow that method only, okay, which I followed, okay. So H1 will be equals to H2 plus dW by dm. So finally you will get the work interaction per unit mass will be equals to H1 minus H2. Okay, so it is seen that work is done by the fluid at the expense of its enthalpy. Okay, means difference of this enthalpy will give you the work, okay, per unit mass for a turbine. Okay, so this way you need to remember. Okay, so H1 minus H2, difference of the specific enthalpy will give you the work done by this turbine per unit mass. So similarly for an adiabatic pump, so turbines are what? These turbines are positive power output devices. You are getting power at the output. You are getting the work at the output, and you are now running some generator. So these are positive displacement. Okay, means positive power output devices. But some devices like compressors and pumps. Okay, so in your home there may be some pump. Okay, to discharge the fluid. Okay, to the higher elevation or higher level. Okay, higher altitude. So pumps are basically runs by motors, you know, isn't it? So these compressors and pumps require power input to run, okay, but this turbine, it is positive power, it gives positive power output. Understood? So here similarly for an adiabatic pump or compressor, so work is done upon the fluid and W is negative. Okay, so here as because works need to be done on the system, means we need to give power to the pump or compressor. Okay, that is why this work term will be negative. Okay, so H1 will be equals to H2 minus W by M. So W by M will be equals to H2 minus H1. So same thing, but the sign is different. Okay, here it was H1 minus H2, here it's H2 minus H1. So the enthalpy of the fluid increases by the amount of work input. Okay, so there are other applications also. So it is your homework. Okay, so for heat exchanger also, so you can find out how you will write down the SFEE equation. Okay, so you will get some other examples also. So just you refer one book. Okay, so in our syllabus only throttle valve it is mentioned, but I have given the examples of turbine, compressor, okay, and the other things also as well. And so you can also search for other applications. So if you find any difficulty, then you may ask, okay, through WhatsApp, okay, and if you just if you are not able to clear your doubts with a discussion with your friends, okay, then you can call me also, no problem. Okay, so thank you dear students for listening. So yeah, I am giving you some time. If you have any problem regarding the previous class also, or for today's class, if you have not understood the concept, then you can ask me. Okay, those who are not having any doubt, you can leave the meeting. Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Yeah, I will be uploading this video lecture in the Google Class. So you just check it, okay? And if you have any doubt, then you can ask the doubts in the comment section also.
Okay, sir.
Okay, sir.
Okay, sir.